Hello everyone, my name is Sadiq Pal and I'm from imcivilengineer.com, and in today's video I'm going to discuss about the shear force and bending moment diagram, how we can draw this diagram and all the procedure that is involved in drawing this diagram. Basically, shear force and bending moment diagram, they depict the variation of the quantities along the length of the member. So if this is the length of the member, length of the beam, then the shear force diagram, it shows the variation of the shear force along the length of the member, and similarly the bending moment diagram depicts the variation of bending moment along the length of the member. So before starting the video, if you have not subscribed to our channel, so please do subscribe to our YouTube channel and hit the bell icon so that you can get the notifications of all the new videos. So basically we have a propped cantilever beam. The propped cantilever beam is a beam in which is a combination of a simply supported beam and a cantilever section. So if you don't know what is propped cantilever beam, you can log on to imcivilengineer.com, and I have written an article about different types of the beams. So here we have this beam with a total span of 40 feet, and it has one force, a vertical force here, one uniformly distributed load UDL here of 2 kb per foot, along with a moment of 180 kb foot. So now about the steps which we will be going through. The first step is identify the section points. So basically what we do is that we start from left towards the right, or from right towards left, whatever is easy for you, and we define various sections at the points we think the force is changing. Like in this point the force is changing, at this point the force is changing, at this moment point force is changing, and this UDL is producing a variation. So in all these variations point, we will first identify the number of sections that we have to draw, number of sections that we have to solve to make this bending moment and shear force diagram. So basically after identification we will cut the section, and we will calculate the shear force within that section with respect to the distance. After finding that those equations, we can draw those equations in terms of ordinates of shear force and bending moment, like it is drawn here. So these are the simple 4 steps. First one is identify the section point as explained, then calculate the shear force and bending moment equation for each section corresponding to the length of the member, and then draw the shear force and then draw the bending moment diagram. So after assessing all the external loads that are acting on it, we can assume and we can conclude actually that first I have to draw a section at this point. Okay, then I have to draw a section here, because this force is producing some change in shear force or bending moment. Here we have a moment, so the third section would be somewhere here, and the last section would be somewhere here. So these are the sections 1, 2, 3 and 4 that I'm going to cut and find out the various bending moment and shear force at that section. So I can say this is the first section, this is the second section. For this section, x goes from 0 to 10. For this section, x goes from 10 to 20 feet. Now for this last two, I have two options. I can either move from left to right, or I can move from right to left. So because it is a cantilever portion, so I can have some trick here, that instead of going from left I will go from right. So the third section would be this one, and the fourth section would be this one. So the same here, that x dash would be from 0 to 10, and here the x dash would be from 10 to 20 feet. So this is how we have to select the sections that needs to be drawn. After identification of the sections, we have to solve each section. So let's start from this one. So for x is greater than 0, less than equal to 10, our section is something like this. And here actually no load exists, but according to the basic assumptions of the shear force, this is the axial force. So using the same equations of equilibrium, summation fx is equals to 0, fy is equals to 0, and summation m is equals to 0. Here only vertical forces exists, so I am taking the downward force in positive. These are the positive forces, internal forces at some point. So I'm taking these forces as positive. So V minus 46 is equals to 0. So from here I can say that V is equals to 46 kip. So here the shear is positive. Now summation m is equals to 0. So I have this length of this section is x. So summation m is equals to 0, according to the which implies that it is anti-clockwise. So clockwise it is producing clockwise. So clockwise is negative, minus 46 times x. This is anti-clockwise, so positive, plus m is equals to 0. That means m is equals to 46x. This is positive as well. Okay, so I can say that when x is equals to 0, m will be equal to 0, and when x is equals to 10, then m is equals to 460 kip fit. So this is the value of the first section. Now move on to the next section. Our next section here is from 10 to 20. You can see here. So for this section, for x is equals to 10 to 20. For that I can draw here it is 46 kip reaction force that was already determined. One is this 60 k fit vertical load, and then no the load is there, so the internal reactions. So again, cutting short, I can say that this minus 46 minus plus 60 plus V is equals to 0, which implies that V is equal to 14. Is 14 negative. So shear force has been calculated. Now the bending moment, as the length of complete section is x and this length is 10, so this length is 10x minus 10. So from here I can calculate summation moment. This is clockwise, so taking clockwise as negative, minus 46 times x plus 60 times x minus 10 plus m equals 0. Solving it, (600) minus 14x. So this is the value of our moment, and for same, when x is equals to 10, bending moment would be 600 minus 140, which is 4, and when x is equals to 20, the bending moment would be equal to 320. So after finding the equation of the moment, I can say that when x is equals to 10, the bending moment would be 600 minus 140. So the bending moment is 460 when x is 10, and when x is 20, the bending moment would be 320 kip. So the two sections has been solved. Now the third section, as you can see here, that the third section is towards right from x is equals to 0 to 10, x dash is equals to 0 to 10. So if we can draw this section when x dash is equal to 0 to 10. For this I can draw the section here, and here no actually reaction is there, but only this UDL 2 K per feet, and here I have this upward force, this one, and this moment. So here upward force would be positive, shear force, and the clockwise moment would be positive. So taking its value of x dash, for here I can say that when v is upward it is positive, so v is upward, this is negative, so it will be downward, so it is negative minus 2 times x dash is equals to 0, so v is equals to x dash. This is the value. So for x is 0, when x is 0, the shear force is 0, and when x is 10, the shear force would be 20. Okay, now the value of the bending moment, summation m is equals to 0. For that I can say that at this point the value of clockwise is positive, so I take this as positive. This is also clockwise, so this will also be positive. 2 times x dash is equals to 2 times x dash into x dash divided by 2, because the resultant of this UDL would be 2x, and it is acting at a distance of x dash by 2, so it would be 2x dash times x dash divided by 2 equals 0, which means m would be minus x square. So this is when x dash is from 0 to 10. Now the fourth section. The fourth section is when x dash is from 10 feet to 20 feet. So let's draw its diagram. So for the last segment I have drawn the section diagram, and here it is. You can see here the 2 K per foot UDL, and here it is the reaction force 54. So the length is x dash, and the x varies from 10 to 20. So it is very important for you that when you are drawing the free body diagram of the section, you must include and do not miss the force, any of the external force, because if you miss any force, then your answer will be wrong. So here I have this segment. I can now solve this segment by saying that summation of x is 0, which is always 0, summation y upward taking positive, this downward, so minus 2 times x is 0, and then this plus 54, which is upward, so it is 0, which means that v is equals to 2x minus 54. So when x is 10, v is equals to 20 minus 54, which is calculated to be minus 34. And when x is 20, the value of the shear force is minus 14. So next, the bending moment. Now for the bending moment, I can say I'm taking the clockwise movement as positive, so this is positive. So I'm taking the clockwise movement positive, so it is positive, and it is also clockwise, so it would be positive as well, plus 2 times x into x by 2 and this is minus, because it is anti-clockwise, so this will be minus 54 times x minus 10. So here it would be m plus x square minus 54x plus 540, it would be m is equals to 54x minus x squared minus 540. So this is the equation of the bending moment. So for calculating the bending moment when x is equals to 10 and for x is equals to 20. So when x is equals to 10, if you put the value of the bending moment, value of the moment for x is equals to 10 will be minus 100, and for x is equals to 20, the value of moment would be 140. So now I have solved all those sections. The first section when x is from 0 to 10, the second section when x is from 10 to 20, and the third section when x dash is from 0 to 10, and the last section when x dash is from 10 to 20. So now I would find out the values and I will draw it on the graph. I'm going to draw the shear force. Now from first section you can see here the value of the shear force is 46k. Whether it is 0 or whether it is 10, the shear force is positive 46 constant. So here I can move upward, I can move here, so here I can move upward, I can move here, this is 46. Okay, so after that in the next section, in this point, in this region, the value of the shear force is minus 14, which is also constant. So after getting there, the shear force is minus 14 and it is constant. Now when I reach here, so there is a UDL coming. So we know that whenever there is a UDL, there will be a linear equation, and the shear force equation would involve some sort of x in its value. Like you can see that in this section the value of the shear force has a value of 2x dash, so it is linear equation, and there it is also 2x. So there is a linear equation, which means that the value will be moving in a linear sort of thing. So from here I can say for this section and for this section, for this one which is a fourth section, the value of the shear force is minus 34 and minus 14. So when x is 10, it is minus 34, and when x is 20, it is minus 14. So we are already at minus 14, and when we are here, we have to move towards minus 34 as we go down. So from here I can say that we will go towards minus 34. Yes, this minus 34, and after that when we go towards x 0 to 10, like here, the shear force moves to from 20 to 0. That here, because of this 54k external load, we move towards upward, and we go there as plus 20, and then we go towards 0 at the end. So this is our shear force diagram. You can manually check here, like here it is 46k, you go upward, here you go minus 60 downward, so it's minus 60, here I move downward. From here to here no load is there, so constant, and then there is a linear equation, there is a linear thing, I move downward. From here 54 kip load goes upward, so minus 34 plus 54, 20 upward, and then here, because it is a cantilever, whenever there is a cantilever the shear force is 0. So now the next step is bending moment diagram. For the first section, we know that when x is 0, the bending moment is 0. So this is the point, the bending moment is 0. And when x is 10, the bending moment is 460. So we move upward like this, 460. From there, our next section, and in that section we know that when x is 10, the bending moment is 460. So here it is already 460. And when x is 20, the bending moment goes to 320. So we move downward here slightly and we goes to 320. And in the fourth section, this one, we see that the bending moment is minus 100 and 140. So that means that we have to move downward when x is 20. This is when x is 0 to 10 and 10 to 20. So for 20 we have to move downward here to 140, and when x is 10 it is minus 100, which means I have to move downward here. But this will not be a straight line because it is a second degree equation, so it will be slightly curved. Okay, here the value is 1 minus 100. Okay, now in this equation, in this section, I know that the bending moment is minus x square, so it is also second degree, so it will be a second degree curve. For here x is 0, bending moment is 0. Here x is 0, the bending moment is 0. And when x is 10, the bending moment would be minus 100. So it will be combined in a second degree curve like this. So this, sorry, this is not the, this is our bending moment diagram. So values are 460, 320, then 140, and then minus 100. So this is a shear force and bending moment diagram. So that's all about our lecture. You can see that our results match with the original one. These are the values that we have started from where we have started. So thanks for watching this lecture and hope you like it.